Light travels through space at a constant speed of 186,000 miles per second. Time, on the other hand, is a relative quantity that sometimes passes more slowly and sometimes more quickly, depending on the observer's point of view and speed. This fact was described by Albert Einstein in his famous theories of relativity. By extension, the physics genius also came to the realization that time stops when the speed of light is reached. In this video, we'll take a look at why this is so and whether we humans can somehow take advantage of this effect. Before we start, we would like to ask you to support our work. You can do that now by hitting subscribe, activating the notification bell, and giving us a like if you enjoy the video. Let's start with the mystery of time and the speed of light. Actually simple, right? The big question of this video, whether time stops when reaching the speed of light, can be explained with this simple sentence. On the level of light, there is no time at all. For a light particle, or in other words, a photon, which apparently travels through space with the speed of light, no time passes. The impression of time arises only on the level of the observers, or in other words, we humans. That space and time are illusions of the mind is a claim not only mystical schools make, but also the great physicist Albert Einstein, who came to the conclusion that the universe is not in truth what we think we see. In all his observations, time actually turned out to be one of the strangest quantities that we know of, even though we usually live with it in everyday life without giving it too much thought. The relativity of time. Let's now take a closer look at these theses. When light has traveled 1 light second, this second has passed only in the perception of the observers. From the point of view of the photon, no time passes. Basically, the particle does not even cover a distance through space. On light level, the whole space it crosses is shrunk essentially to zero. Now the exciting question is whether we humans can also experience a standstill of time when we reach light speed in a vehicle like a spaceship. Theoretically, yes, but practically, there are 2 hurdles here. First, we would have to achieve an acceleration of 186,000 miles per second. If we were then traveling at the speed of light, time would also stand still for us in the spaceship compared to the surrounding matter. The fact that it does not come to a complete standstill is simply due to the fact that a spaceship and a human body can never completely reach the properties of light despite the speed of light. Forces like the rest mass of matter, resistances, etc. remain. The second problem is that it's currently impossible to accelerate matter to the speed of light without consuming an amount of energy that approaches infinity. In plain language, this means reaching the speed of light is not possible using classical physical quantities and mechanical drives. However, this does not mean that humans will never travel at the speed of light or even faster. Scientists are currently researching ways to bend space-time and use negative or exotic matter to achieve acceleration by manipulating forces. Does light really have a speed then? At the photon level, time stops from our point of view. We cannot tell how a photon experiences time, or if it experiences anything at all. Einstein found out about 100 years ago that the speed of light is the only constant and not relative quantity in space. However, the behavior of light in its smallest particles is again anything but constant. An important aspect of velocity measurement is also a relative and not a constant quantity. Time. Velocities indicate the distance that something, in this case a light particle, travels within a certain time in a measurable space. But also, space could be not as linear as we imagine it on Earth, and the calculations of physicists must always start from an edge of space. With respect to space, we don't even know yet if these boundaries exist. If you follow our videos often or subscribe to our channel, you probably know that the latest findings of the James Webb Space Telescope have found that previous theories of distance measurement based on light shifts in space are currently under scrutiny. Either there were mistakes here, or with the Big Bang Theory, or there really are galaxies which should not exist at all. On Earth, experiments showed that light spreads with a certain speed. However, at present, we know too little about the real nature and origin of the cosmos to know for sure if the observations on Earth also apply to every corner of space. If light has to pass through thin forms of matter, it slows down minimally. So we can't exclude that the speed of light behaves differently somewhere in space, even if Einstein thought that the speed of light is an irrefutable constant. Quantum physics and photons are nothing more than quanta, prove that light is not constant in the microcosm of the small particles. Rather, it seems to be physically neither at a certain place nor at a certain time. This could support theories that the impression of motion, space, and time exists only in our perception. According to the latest findings, space could also be something like a gigantic holographic projection. What exactly the connections between the level of light and the material world are, researchers do not know at present. Just how crazily time behaves and why it stops when humans reach light speed, we'll show you now. The phenomenon of time dilation. For the following thought experiment, we need a simple reference frame for time. Suppose a photon bounces between two horizontal mirrors. Since the speed of light is a universal constant, the time that elapses between two bounces is always constant. In this case, one bounce is 1 unit of time. Now we transfer the picture to an everyday scene. We imagine a person who goes to his lunch break and drinks a coffee and eats a roll. His break lasts 100 time units. At the same time, NASA astronauts are happily testing a spacecraft that has already reached half the speed of light. The man as well as the astronauts of NASA have a clock which corresponds to our photon clock, and thus the same length of time interval. The astronauts do not have the feeling of moving on their flight. They sit in their chairs, and only when they see the world passing by would they have a sense of movement. From this point of view, the man on his lunch break would race past the resting astronauts at half the speed of light. Thereby, he sits quietly at a table in the cafe. From the point of view of relativity, physics, and time, it's impossible to say which of the two views is the correct one. The time shift we are about to show you is real for the astronauts, even if in reality, the man is not moving at half the speed of light. The photon clock of the man in the cafe would also move with half the speed of light as seen from the spaceship. By the angle which then arises from the perspective of the spaceship and the speed, the photon would cover a much longer way between the two bounce intervals. So the time unit on the photon clock of the man is then further apart. Since the astronauts aboard the spaceship can only observe the events with their own photon clock, the time units would still match the initial image. The photon is moving up and down, and the amount of time it takes for this movement has remained the same. Since the speed of light is the same in each reference frame, the distance the photon travels in both clocks is theoretically the same. Nevertheless, the astronaut's clock ticks faster than that of the man in the cafe. If the man finished his lunch break after 100 time units, much more time units would have passed for the astronauts, because the photon on their clock had to travel the direct way and not the way via the extended angle. On the photon clock of the astronauts, 120 time units could have passed. This phenomenon is called time dilation in physics. If a person moves past an observer, it can be observed that the clock of this person ticks much slower than that of the observer. We can also illuminate this effect a little more deeply. People are made of matter, which basically consists of charged particles called electrons and quarks. The particles form matter, in which they exert a force, and this comes about in the exchange of photons. We know this effect as electromagnetism. This force is not only behind the formation of elements in matter, but also behind all kinds of movement or life. Breathing, thinking, eating, and metabolism have to do with these forces. During all these actions, photons are in motion, which means they travel distances so that interactions, motion, and force can take place. As the man in the cafe moves past the astronauts at tremendous speed, not only do the photons in his clock take longer to tick, but so do the photons in the electromagnetic interactions of his body. Viewed from the spacecraft, the man's hand would move more slowly to his mouth at lunchtime, his heartbeat would be slowed, and even cell division would proceed differently. If the speed of the spaceship increases to the speed of light, this time delay would be so great that the man's heartbeat and breathing would come to a virtual standstill on Earth. Time and the sequence of events would be suspended. Meanwhile, not much changes for the man on Earth. His heart would continue to beat normally, and the next day, he would again be sitting at his lunch break for exactly 100 time units. From the perspective of the spacecraft, however, this phenomenon means that the man on Earth would age more slowly than the astronauts. Research continues. Currently, scientists are still not sure how the phenomenon of time dilation would affect astronauts on long space flights, or perhaps we have not yet properly understood the dimension of time. Among other things, scientists are currently working on slowing down light to the point where it no longer travels at the speed of light. At Imperial College in London, this is said to have already been achieved. Light was slowed down by a factor of 15 million and then only traveled at 66 feet per second. But if we now remember that light itself probably knows neither time nor space, and if we succeed in slowing light down to such an extent that it virtually matches our speed, we might be able to build light gates that allow us to travel through time and space. Exciting, isn't it? Now tell us what you think of the fascination of light and its possibilities. Do you also think that light could be the key to the universe, or at least to travel within the cosmos? We look forward to your contributions to the topic in the comments, and thanks for watching.